Hi, I'm Jillian, and today we'll be looking at number 10 from section 3.6 in our book. So let's get right into it. The problem. We're looking at the Goldbach conjecture, which is that every even integer greater than 2 can be expressed as a sum of two, not necessarily distinct, prime numbers. Right now, we don't know if it's true or false, and it's been something we've been working on since 1742, a long time. So getting right into it, we've got part A. Write 50, 142, and 150 as the sum of two prime numbers. So this is pretty simple. I wrote 50 as the combination of 47 and 3, 142 as 59 and 83, and 150 as 53 and 97. These are all prime numbers. If you divide 47 by 7, you don't get anything good, and the same goes with the rest of these numbers for their ending digits. So part B, we ask to prove the following. If Goldbach's conjecture is true, then every integer greater than 5 can be written as a sum of three prime numbers. So we're going to go ahead and start that proof. We're going to assume that Goldbach's conjecture is true. We want to show that every integer greater than 5 can be written as a sum of three prime numbers, and I've chosen to continue by induction. So our base case is normally looking at n is equal to 1, but since it has to be greater than 5, we're looking at n is equal to 6. So 6 can be written as 2 plus 2 plus 2, since the primes don't have to be distinct, but if we wanted distinct primes, we could also write 6 as 1 plus 2 plus 3. Now, since we've proved this base case, we're able to move to our inductive step for n plus 1. So n plus 1, we've got two cases. Case 1, n is odd, and that means n plus 1 is even. So we've got n plus 1 is equal to n minus 1 plus 2, and since n minus 1 is greater than or equal to 5, it can be written as the sum of two prime numbers, as in Goldbach's conjecture, p and q, such that n minus 1 is equal to p plus q. So by algebra, we have n plus 1 is equal to p plus q plus 2, which is a sum of three prime numbers. Moving on to case number 2, n is even, which makes n plus 1 odd. So we have n plus 1 is equal to n minus 2 plus 3, and since n minus 2 is greater than or equal to 4, it can also be written as the sum of two prime numbers, p and q, such that n minus 2 is equal to p plus q, and n plus 1 is equal to p plus q plus 3. So in both cases, we see that every integer greater than 5 can be written as a sum of three prime numbers as required. So moving on to part C, we are asked to prove the following. If Goldbach's conjecture is true, then every odd integer greater than 7 can be written as a sum of three odd prime numbers. So getting into this proof, we're once again assuming Goldbach's conjecture is true. Just to make it super easy and clear, we want to show that every odd integer greater than 7 can be written as a sum of three odd prime numbers. And once again, I've chosen to continue by induction. So our base case is 9. Similar to part B, since it has to be greater than 7 and be odd, the next available number as n is 9. So 9 can be written as 3 plus 3 plus 3, since the primes don't have to be distinct. And having proved this, we can move on to the inductive step for n plus 2. So this is just one case, so we have n plus 2 is equal to n minus 1 plus 3. Since n minus 1 is even, it can be written as the sum of two odd prime numbers, p and q, such that n minus 1 is equal to p plus q, and then n plus 2 is equal to p plus q plus 3. And thus, any odd integer greater than 7 can be written as a sum of three odd prime numbers as required. That's all I have for you, and I hope you enjoyed.